Hey,
Yeah?
you ever wonder why we're here?
Like, metaphysically? Or.
No. I mean, it's one of life's great mysteries, isn't it? I mean, why are we here? Are we the product of some cosmic coincidence, or is there really a god watching everything? You know, with a plan for us and stuff. I don't know, man, but it keeps me up at night.
Oh, I thought you meant, why are we here? In this canyon? But that's a good question, too. Humankind's smartest has been trying to answer that question since the dawn of time.
Well, I mean, what progress have we made? What answers have we found?
There's a theory out at the moment. It's called string theory. It's a bit complicated. You might not understand the concept.
But I want to understand. Help me out here.
Well, you're kind of an idiot.
And you're kind of obnoxious, but I put up with it. Alright? If you can't just tell me, I challenge you to make an 8-minute long video explaining string theory.
I don't know. It's difficult to grasp.
Chicken.
Alright. You're on.
No, 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 no! You're wrong! A particle is there because it is, not because you measured it to be there.
Wrong. Electrons and protons move so fast that their location is like a wave of energy. At any given time, their location is smeared throughout space, making it a bit hard to predict the crazy paths they might take.
That's just wrong. How can one particle be a wave? That's like saying I could smear out into a liquid shape at will.
You sure can, just hold still.
Then convince me. How does quantum mechanics deal with this? Is it a wave or a particle? Enlighten me.
Certainly, but first you have to guess which one it is.
No.
Oh, come on. You want to?
No.
Please?
No!
Please? Ah! Okay, I'm sorry. Okay. Well, as you know, quantum mechanics deals with the behavior of all subatomic particles. Quantum mechanics says that when searching for the properties of such a particle, like a photon or electron, it's a wave and a particle. It can be either one depending on what kind of experiment I do. Sadly, if I do an experiment to find the speed of an electron, I'll lose the location, giving my electron the properties of a wave. If I find the location of an electron, I'll lose its speed, giving my electron the properties of a particle.
So, which is it?
It's like I said before, it is what you measure it to be. If I measure its speed, it has the properties of a wave, and vice versa. A guy back in 1927 named Werner Heisenberg.
Wait, was his name...
Heisenberg.
Yes. Anyway, Mr.
Heisenberg.
dubbed this as the uncertainty principle. With it, you have to account for all types of uncertain variables.
See? There's your blasted uncertainty again. What use is quantum physics if you have to calculate chance and probability into your subatomic math? That's a guiding principle in your science. The uncertainty principle. This is physics. How can you dare be so vague with your mathematics? In fact, the forefather of my science had the best thing to say to this.
God does not play dice with the universe.
I doubt he sounded that silly.
Coming from the floating bowling ball, you know Einstein, one of humanity's shining examples of intelligence. He, like myself, was unwilling to let go of classical physics Newton founded.
Oh my! An apple!
Einstein, who had built his work from Newton for so long, refused to accept the strange and unexplainable behavior your physics undertakes, and rightfully so.
Which the father of my theory, Max Planck, had no problem doing. He gave birth to quantum physics when he set out to quantize electromagnetic energy. Quantization, as you know, is a procedure for building quantum mechanics from classical mechanics. He even got a Nobel Prize in physics because of it.
First of all, his name is Planck. Planck! What, did he make up his theories with his buddy Johnny 2x4? Secondly, wasn't he a Nazi?
No, actually, he very strongly protested against the Nazi regime and helped out a couple Jewish scientists. He even met Hitler and tried to dissuade him from being all evil and all, but, you know, he's Hitler. Planck also established the Planck length, which is humanity's smallest unit of measurement.
You forgot to mention that Planck didn't even intend to invent quantum mechanics. When he tried to quantize electromagnetic energy, he didn't expect it to work. He thought it would throw his life's work on quantum theory out the window, though in fact it only cemented everything he'd done permanently.
Which wasn't helped by the Nazis bombing his house in 1944.
What? No! No! Nazis! No! Ah! No! My house! No! Ah! Ah!
Oh my! Another apple!
Despite that, Planck's revolutionary work paved the way for thousands of scientists. Ha! And you say your theory of relativity is useful.
Actually, the term relativity has to do with perspective, not chance. It's far more exact science than your absolutely strange quantum mechanics.
True, quantum mechanics is strange, but that does not detract from its uses. It's responsible for nearly everything electronic in our day-to-day lives. Cell phones, computers, and even the visor you're using to surf on Facebook.
I'm not, but it doesn't work.
Back in the days of telegram without quantum physics, subatomic particles behave in a bizarre way, but we can manipulate them to our advantage using things like the Standard Model. Circuit boards and chips manipulate electrons to function, a feat that was possible before my field came along.
But it doesn't work.
Oh yeah? Tell that to your camouflage. We made that by bending subatomic light particles called photons. Shoot! Tell that to me! Do you know how many particles go into transferring consciousness into a machine? Quantum mechanics has been proven to be right again and again. Don't tell me that it doesn't work.
That's not what I meant, you spineless bowling ball. It doesn't work when applied to real-world objects. The physics of it simply do not work. So explain to me why quantum mechanics breaks down when objects get too big.
Well, we talked about quantization.
Yes, but quantization is a flawed process. Quantum mechanics covers 3 of the 4 fundamental actions in our universe: electromagnetism, the strong force that holds protons and neutrons together, and the weak force responsible for radioactive decay. It does not take gravity into the equation at all.
Theory of relativity deals with gravity, doesn't it? You're the clown. Teach me all about it.
I'm a scientist, ball bearing. You're the clown. Anyway, when Albert Einstein sat down to work on gravity, he had a problem. How could he truly explain gravity? Newton had established how gravity on Earth functioned, but his theory was incomplete. It didn't cover how it functioned in space, how massive entities were able to stretch across empty nothing and physically affect other spheres of matter. Here was his theory. Come here, sit in this water. Imagine space and time as a single entity rather than two separate measurements. Now imagine you are the sun and this object is a planet. The water you are inhabiting is space-time, a flat geometric surface that you are making a depression in. This depression creates a valley in space-time, and this is what makes the planet orbit you.
And this is real? Space-time is a real thing, where the two are together.
Absolutely. I have the math to back it up. The problem is your petty quantum mechanics does not account for this. It completely ignores the physics of the macrocosm.
Whatever, I'm getting out of the water. You're just trying to short-circuit me because you know I'm right.
You're wrong. Your physics are wrong.
No, yours are.
No, relativity is right.
Quantum mechanics!
Relativity!
Children, please. I have a solution for you. I have a theory of my own that will solve all your troubles. It will end your bickering in but an instant. We begin with a question of the highest importance, of the most intense gravity.
I get it, cause gravity and I'll shut up now.
We begin with a question of the highest importance, of the most intense gravity, a glorious question, asked to us by our Greek forefathers, by our immaculate ancestors. Democritus of ancient Greece, a wonderful philosopher from days of yore, asked us, what is the most basic, undivisible, unbreakable particle that composes all of matter?
The atom!
At his time, absolutely. But you know that ladder has more rungs to be found. The nucleus is formed by protons and neutrons, which are formed by quarks and leptons. The answer? The one undividable particle? The reason behind all the diversity within our universe? Strings.
Strings?
Yes! Within everything is a bunch...
Great. The end-all be-all of everything is a vast amount of tangled computer cords. Bravo, physics. Bravo.
Oh, hush. This wondrous, encompassing, all-solving theory was developed by one of the smartest men we know.
Planck?
Einstein?
Japanese physicist Michio Kaku.
Relativity.
Quantum mechanics.
Relativity. Clean up your relativity.
Children, please. I have a solution for you. We begin with a question of the highest importance, of the most intense gravity, a glorious question asked to us by our Darmakazuze, Jamakuze, no Jadi, Kara, Sujugod, Jose, Wa, Kojigargazijas, Kara, Mashali.
I don't know what you're saying. What are you saying? Speak English.
Surumoto, Shinogakete, Bubanen, Odobajakate, Rashuk no Wadazoka.
In all seriousness, Michio Kaku is a Japanese American, and he's quite fluent in English. It's also wrong to give him, or any one person, all the credit. String theory was formed by many scientists, each contributing their own work to the theory. To help you visualize string theory, I'll need a volunteer. Volunteer! Yay! Volunteering! Woo! Prepare to be vaporized. Their work says that these strings within subatomic particles vibrate at specific frequencies, which give each particle the unique properties they possess, like their mass, speed,
charge, and weight. But there's a problem. Strings can't exist in only 3 dimensions. The mathematics only work when 11 dimensions are factored in. Dimensions being our known length, width, and depth objects in our universe have. This corroborates with past theories, saying that there are dimensions curled up so small on the subatomic level that they are invisible to the naked eye. String theory will tell you that these strings are tucked inside of these extra dimensions.
Hey,
Yeah?
wasn't the whole point of this video to explain string theory to him? So how big are these strings supposed to be?
Your bowling ball here mentioned the Planck length earlier, our smallest unit of measurement. Here, to scale just how small these are to you, check the feed I've sent to your visors.
Dude, this is small.
You also said that your quantum mechanics and your general relativity won't work together. String theory will fix that. Along with the Higgs boson particle, another particle's existence has been theorized, called the graviton. This field of gravitons inhabits all of space, explaining the discrepancies that you discussed.
You mentioned the Higgs boson earlier, right? So these boson particles, the Higgs and the graviton, are comprised of string wads or chords or whatever? How might we go about finding these?
Come with me, I'll show you.
Oh, you're going to show us a massive, enormous, glorious, gigantic, super hadron particle, right?
No, just step in the teleporter. Just go in. In fact, your quantum mechanics made this possible. Welcome! Welcome all!
Wait, this is...
That's right! Welcome to my massive, enormous, glorious, gigantic, super hadron particle collider! In space!
Yeah, so totally called that.
Shut up. Earlier, you asked me, how might we go about finding these strings? This is your answer. A massive particle cannon with enough power and energy to smash subatomic particles together.
And what does that accomplish?
Follow me. I'll show you. Now, we'll pretend that these two machines are subatomic particles. The purpose of the Hadron Collider is to speed two particles around as quickly as possible until they reach a speed so great that the collider can put the two together, with destructive results. The two particles send out debris in every direction. Remember the unknown dimensions we discussed earlier? The explosions of the particles send out debris into these dimensions, helping us to find them and analyze them. There's a particle that's become famous quite recently.
The Higgs.
That is hidden in these dimensions. This particle is omnipresent, hidden in everywhere and everything. Interaction with this field of boson particles is what gives things their mass. Once the Higgs can be researched, the next step will be finding the strings, and then the graviton, solving the issues you two have been having this entire time. Research like this is the next step for humanity. As a race, our goal has always been to truly solve the everlasting question, why are we here? We've never known before, but the answer could be just around the corner.
Yeah, whatever. What have you actually found?
Well, we found evidence of the Higgs.
So, you're still not entirely sure of these bosons? Or these strings? Or these dimensions?
Well, no.
So, despite your convincing arguments with the massive, enormous, glorious, gigantic Super Hadron Particle Collider...
In space.
Yes, despite that, all of the science behind these strings are purely conjecture? None of it has been proven yet, or even slightly indicated? Perhaps you shouldn't speak of this as fact.
Yeah, you got as much proof as Democritus did when he and his philosophers thought up the atom.
What? After everything I said to you, after everything I've done, you know what? Forget you guys.
Well, if he's wrong, quantum mechanics is definitely right.
That is a fallacy. Plus, general relativity is the more truthful of the two.
My theory is based on mathematical fact.
You're a floating ball with the most irritating voice since Justin Bieber.
You can't really compare me to that.
I just did.
Hey guys. You'll wanna know what I made this out of?
What?
Strings!
Just a city boy, living in South Detroit. He took the midnight train going anywhere. Street lights, leave it. I don't know the real words, so I'm going to ad-lib some crap. Yeah. 'Cause I'm so amazing.